Oh, good.
Okay.
That's working.
Yeah, so then the screen. And now presentation.
Okay, and back and forward. Good, good. And is this microphone working?
Yeah,
it's flashing?
So. I think so.
Flashing is good.
Well, we can just double check.
Hello, hello. Testing, testing. Testing 1, 2, 3. Testing 1, 2, 3.
Yep. So just yeah, she's checking the online.
I'm ready.
Okay, so today we have Dr. Ned Wontner. He's from Amsterdam University, and his research interest is in history of mathematical logics and topology, and a method of mathematical change and descriptive set theory, and too many other things. And he graduated from, I think, Amsterdam University, and he got his master at some famous university, Cambridge University, and he got his bachelor in Oxford University. And today he will tell us about this descriptive set theory, the analysis, and its generalization to higher cardinals. Please.
Great. Well,
I think, sorry to interrupt, just for full disclosure for everyone in this room, this talk is currently being live streamed on Facebook. So yeah.
yes.
Yeah.
Hello everyone online. And hello everyone here in the room. Thank you all for being here. I should first thank the organisers, both the organisers here and also from the from the Logic Society of Malaysia, especially Zhu Yao, who was crucial in setting up these talks. So I'm going to talk about descriptive set theory, and I'm going to have two parts to this talk. The first part is more or less historical, which is going to try and take you from the beginning of descriptive set theory up to sort of contemporary research areas. And then in the second part, I'm going to have a short break, and then in the second part, I'm going to talk about some of the things that I've been working on. It's going to be a non-technical talk in the sense that I'm not going to present proofs or even kind of proof techniques. It's going to be more about ideas, motivations, goals, things like that. And we'll see some theorems along the way. Okay. So, first part, we're going to talk about what we call classical descriptive set theory. So that basically means everything up to 1950, 1960, something like that, and how this came out of real analysis and measure theory. And the things that I'm going to look at in particular are Baire functions, Borel sets, analytic sets, and regularity properties. I'm going to go through what each one of these is meant to mean in this context, so you don't need to remember those at the moment. And then in the second part, I'm going to talk about generalized descriptive set theory. So having set up descriptive set theory, I then talk about what it is to generalize it. Link this to the thing that I've been personally working on, which is generalized real analysis. And that is the introduction of a new field here in the mathematical sense, i.e. an algebraic object closed under certain properties, and how we can generalize the theorems of classical real analysis that you would learn in, say, a bachelor's real analysis course to this larger, more infinite object which we call the kappa reals. Okay, so that's the plan. What's descriptive set theory? Well, it's mainly about sets of real numbers which have nice descriptions. And what exactly nice descriptions means is going to be one of the main things that we're going to be thinking about in the first part of this talk. It's closely linked with real analysis. And in fact, in the early history, the progenitors, the people who started off descriptive set theory, were real analysts. They wouldn't have thought of themselves as descriptive set theorists, at least not at that time. So 3 people who will come up a lot in this talk, all French, Emile Borel, René-Louis Baire, and Henri Lebesgue. And that's Lebesgue off of Lebesgue integration, Lebesgue measure, that sort of thing. Yeah. The big Lebesgue. Okay. We need to detour away from sets to functions for a moment. So at the end of the 19th century, the fashionable thing in some mathematical circles in continental Europe and wider were the arbitrary functions. So until this point, let's say until the beginning of the 19th century, function typically meant something with a very, very prescribed behaviours. So algebraic functions, x squared plus 4, or trigonometric functions, or maybe combinations of those. And it was only in the 19th century that we get this idea of the arbitrary function, that is just any collection of inputs and outputs. Nothing, no behaviour, just inputs and outputs. Okay, brilliant, fascinating idea. And these are the 2 people who were at the heart of that. There's Dirichlet and Riemann, they're German. I thought stamps rather than pictures in this case. I think we should all aspire to be on a stamp. All right, but arbitrary functions, because they're arbitrary, are very difficult to analyse. They don't have the properties that you would be interested in if you're a real analyst or a measure theoretician. We don't in general expect them to be continuous, differentiable, integrable, any of these properties which kind of well-behaved functions we expect to have. Arbitrary functions don't have that. So what we want to have with our kind of real analyst hat on is a notion of niceness which isn't just it's got the property we want, it's kind of we've defined the function in such a way with such and such a complexity, and we know that if we use that kind of complexity we're safe, we're continuous or differentiable or integrable or whatever. So I'll expand on that in a moment. Okay, but why are we talking about functions if this talk is on descriptive set theory? Well, when we're thinking about sets of real numbers, there's an important sort of duality between sets and functions of real numbers. Here's an example. So we've got this red function. It's different from some functions that you might deal with in that it's got these discontinuity points. Right? It's got 4 discontinuities. But if we have a nice definition of the red function, we can immediately get a nice definition of the green set. And we can just say it's the set of discontinuities of the red function. Right? So if you've got a way of having a nice definition of a function, you can obtain nice sets of real numbers in various ways. And the other way, you can also work from sets to functions. It's a little bit more difficult, but it can still be done. Okay, so that's why we're also interested in functions here. Okay, so first of the bits of classical descriptive set theory, Baire functions, named after Baire. He didn't name them after himself. We've now named them this. It's a classification of real functions into a hierarchy. So we start at the bottom with the continuous functions. You can define that however you like, with epsilons and deltas, with a topology, doesn't matter, always the same class. Then we want the pointwise limits of sequences of real functions. So you have a sequence of of continuous functions rather. You have a sequence of continuous functions. You take the pointwise limit. If this also defines a function, so if it converges everywhere, you say that this new function is level 1. Carries on like that, so that at an arbitrary level, we can take a sequence of functions from any level below, take the pointwise limit. If we get a function, that's of the new level. So here's an example. This is the square wave, and the square wave, it's the pointwise limit of a sequence of continuous functions, and you can, so you know that at most it's level 1, and in fact it's exactly level 1 because it's not continuous. Right, so this is the sort of thing that the Baire functions describe, and they are a hierarchy of complexity for functions. But are they interesting? So I've defined something. Great. Is it interesting for real analysis, which is our kind of the thing that we're keeping close to all the time? Well, potentially not. I'm more interested. So here's a problem. We know nothing about the algebra on this hierarchy. We don't know if we can add functions and we stay at the same level. We don't know if we can multiply functions. All we know about is their limit behavior, that if you do a limit, you go to the level above. That's the only thing we know. But in general, in real analysis, in measure theory, we're interested in combining functions in other ways. Okay, so recall Rolle's theorem. Rolle's theorem says you go through here, you go through here, you're differentiable. At some point, you've got to have derivative 0. To prove this, the classical proof of this uses that the algebra of differentiable functions, the differentiable functions are closed under taking away scalars and dividing. So not a big strong algebraic property, but something. And we don't yet know this for the Baire functions. So we can't even do this most basic thing, this Rolle's theorem, for the Baire functions. So here's a more interesting, possibly more interesting definition. They're called the analytically representable functions. Name doesn't matter. It's the smallest set of real functions which is closed under constants, projections, sums, products, and taking limits. So it contains the constants, contains the projections, and closed under those properties. The advantage of this is we can do that sort of stuff, right? So we know that if we're in the analytically representable functions, we can do these kinds of proofs. Okay. This is nice algebra of functions. Here's the theorem. That's actually just the Baire hierarchy. So here we have a nice definition. On the other side, we have a nice hierarchy of complexity. And the theorem of descriptive set theory here is that actually these are characterizing the same class of sets. So we can motivate it. We can say it's interesting because we can do stuff on this side. And then we can place these functions into a hierarchy of complexity using the stuff we saw on the slide before. So that's an interesting observation. And you might have feelings that this is close to measure theory, and we will expand on that in a moment. So this gives us a notion of definability for interesting functions of real analysis. So the ones that are the continuous functions are the simplest, and then the level 1s are a bit more complicated, level 2 a bit more complicated. Right? We've got this hierarchy. Okay, so that was all functions. Let's think about sets for a moment. Borel sets. This is the standard Borel sets, if you remember from measure theory. So this is the smallest sigma algebra containing the open sets. Sigma algebra is closed under countable unions plus closed under taking relative complements. All right, that's how you normally define it. You say smallest sigma algebra with the open sets. But there is a way that you can define this in terms of a hierarchy. So at the bottom we have the open and closed. At the next level we have the countable unions and countable intersections of open and closed. That's F sigma G delta. You carry on up, and at level alpha you take countable unions and countable intersections of anything of a lower level. Right? Hierarchy. Again, that's a picture of how it works. So more complicated going that way. And the theorem here is this hierarchy does in fact characterize the Borel sets. So we have our sigma algebra definition, we have our hierarchy definition, they coincide. So we've now got a hierarchy of complexity for Borel sets. Something that I didn't mention about the Baire functions, it's true of the Baire functions as well, but it's nice to, this is a kind of classic result of descriptive set theory, is that the hierarchy is actually increasing. It's, it doesn't really matter how far, infinitely far. So level 1 is distinct from level 2, is distinct from level 3, is distinct from level 4. So we have, it's not like it finishes at level 10 or whatever. We have actually defined an infinite hierarchy of complexity here. So that's good. But if you might be thinking, okay, so we've had this thing about functions, we've had this thing about sets, what's going on? In fact, these are the same hierarchy. You have to do a little bit of fudging because one's a hierarchy of sets and one's a hierarchy of functions, but there's a natural, well-motivated way of doing that. And if you do this this way of transferring this hierarchy into a hierarchy of functions, you end up with the very same hierarchy. So this looks like we're tracking something, a genuine mathematical phenomenon. It doesn't look like it's an arbitrary definition. We've done two totally different things, and they come up with the same hierarchy. Okay. All right. So we've got a hierarchy of complexity, namely the Borel sets. Can we get more complicated than the Borel sets? Right? Is there any point getting more complicated than the Borel sets? Maybe the Borel sets are good enough for whatever we want to do. Well, here's something that we do all the time in mathematics. We take the image of a set under a function. We just look at the image, the range. So this is not restricted to real analysis. This is all over the place. You just want to look at the image under a function. And we call this analytic. So if your set is the image of a Borel set under a continuous function, we call it analytic. Lebesgue thought that every analytic set is Borel. He thought that this doesn't get you any more complexity. And it's easy to see why he might think this. So let's take a Borel set and a continuous function and see this in action. So think about the closed sets of Borel. So think about the closed set 0, 1, and think about the function x squared plus 1. So let's plug in 0, 1 to x squared plus 1, and we're going to shift, and we just get 1, 2. So that's closed again, so that's Borel again. And often, typical uses of continuous functions over Borel sets will deliver you a Borel set. But it's wrong. In fact, analytic sets are more complicated. The particular characterization is that a set is Borel if and only if it's analytic and also its complement is analytic. Okay? So what does this mean? This means that being Borel is more restrictive than analytic. There are more ways that you can be analytic, so there are more analytic sets. So, it's this interesting thing about complexity, which is when you rise up the complexity hierarchy, because there are now more ways that you can form a set, there are more sets of that form, right, in some natural way. Okay, so what this means is we have the whole Borel hierarchy, and then
Can I ask, is that theorem clear that there's a non-Borel analytic set?
Does this theorem make sense? Not by itself, but you can. There are.
Okay.
So may I ask, is it true that any non-measurable set is not analytic set?
Every non-measurable is not analytic. Yes, all analytic sets are measurable. We'll get to that. And the question here is this too complicated? So we had the Borel sets, we say they're nicely behaved. We have the arbitrary sets, in some ways they're too complicated. Have we gone too far? Have we tried to find a middle ground but gone too far towards the end which is unconstrained? And the answer is no, they still have nice regularity properties. This links to your question. So what is a regularity property? A regularity property is a thing that we would want a set to have for the purposes of measure theory or real analysis. So I'm going to name three. One of them is being Lebesgue measurable. But the first one is this property of Baire. So this means that you're almost open in the sense that there's an open set, and the difference between your set and the open set is basically topologically null. There's more or less empty. Actually, the difference is slightly more complicated than that, but basically you're very, very close to an open set. The second one is the perfect set property. So this says that your set is either countable, which in the context of the reals means really small, or contains a perfect set. So that's like saying that there's some kind of open subset within it. Right? So the first one is you're almost open. The second one is you sort of have an open set inside you somewhere. And the last one is indeed Lebesgue measurability, which is just the Lebesgue measurability from measure theory. If you are used to Lebesgue integration, there's an easy way to work out whether a set is... Lebesgue integration is on functions. We're talking about measurability on sets. There's an easy way to, if you're more used to integration, to work out whether a set is Lebesgue measurable. So suppose this is your set. Make it into an identity function. If this identity function is Lebesgue integrable, then your set is Lebesgue measurable, right? So Lebesgue measurability is actually simpler than Lebesgue integrability. Okay, anyway. And there are loads more of these. It is not interesting to go into for the purposes of this talk, there are reasons that you might be interested in them. But this is just to give you a sense of the sorts of things that a regularity property is. Okay, now using standard set theoretic background assumptions, so just like using ordinary mathematics, there's a set which doesn't have the Baire property, there's a set which doesn't have the perfect set property, and there are sets which aren't Lebesgue measurable. But every analytic set does have these properties, right? So not only does every Borel set have these, even the analytic ones, the more complicated ones, also have all of these properties. So this suggests that the analytic sets are still good, nice, for the purposes of real analysis and measure theory. It doesn't seem like we've gone too far. So it seems like the analytic sets are still, in the realm of what we might reasonably deal with. So this brings us up against another question, which is how far do you have to go to stop having these regularity properties? If analytic is still good, how complicated do we need to go before things get bad? And there are whole other hierarchies here that go far above Borel, far above analytic. Increasingly more complex, strictly more complex, so these are strict hierarchies still. And this is actually one of the contemporary research areas. So we've now kind of worked our way up to what people are working on now. For the three regularity properties I mentioned, it's known how complex you need to go. Turns out to be different for different regularity properties, and it also turns out to be not that much far above analytic. 1 step, 2 steps above analytic. So analytic looks like a sweet spot. But this is something that people are working on in various ways, on other regularity properties, for example.
Can I
Yeah, please.
I understand what levels mean. So you mean the next level would be taking continuous image of an analytic set, like continuous function?
So the composition of two continuous functions is continuous.
Right, that
So,
doesn't help.
so that doesn't help. You take a complement, and then you do a continuous image.
Oh,
And you
yeah.
take a complement and take a continuous image. Yeah. And I'm now just going to mention some other things that people do in descriptive set theory. Now contemporary research areas of descriptive set theory. So some people work on uniformization. That's sort of to do with choice functions. Some people link descriptive set theory with computation or with game theory. That's a fascinating area. Other times you work on other topological spaces. So far I've always been talking about the real numbers, but what happens if you look at other topological spaces? Some people look at the effect of changing your background assumptions, so your background set theoretic assumptions, alternatives to ZFC, if that makes any sense to people. That's actually a very big area. And the last one, which we will see in the second part of the talk, is generalizing to higher cardinals. So I'm going to take a 5-minute break there for some water. I'll see you again in 5 minutes.
Oh, okay.
So lag. I think lower a bit.
Lower a bit, okay.
Yeah, very lag. Now it's okay. I scared to move it too much because when just now when I tried this morning, move too much, the whole live stream disconnect. So I very scared.
Okay, because just now this part cannot see clearly, the right-hand side upper part.
Oh, I think make it higher again.
Make it higher. There is a water bottle.
Yeah, later he's drinking. Oops.
Okay, well, we'll go to the mountain and go to the technical the other one
Now we need the part where I fix it so lag.
Like.
Oh, okay, now it's not good.
I think I put here.
The one above is
Cannot.
there are lots of them.
I think just now it's good.
Sort of in one direction is the other direction.
Because it's lag.
Yeah, I need to wait for it to update.
Okay.
I think just see from here. Yeah. Okay. You've got a nice infinite loop there. Yep. We also said going there. Yeah, he's watching from. Yeah, Juya's watching now.
Excellent.
What's he doing? Julia? He's in Atlanta still?
I don't know.
Oh, is that Atlanta? Maybe it's
Atlanta. Yeah,
it's
he's somewhere in
Atlanta.
the US.
Yeah.
Last I heard him.
Okay. Is the live stream still going?
Yep, still going.
Okay. Then I will start part 2. Okay, part 2. This is we're not going to talk about this, but this is, I just like it as a picture. This is the different properties of infinite cardinals. So these kind of measure the sizes of infinities, which will come up, but we don't need to go through it.
1.
Yeah, 0 equals 1. It turns out if you assume that
Large, very small.
small, this is small, and that is, well, so large it's contradictory. Yeah. 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 Okay. I've been lying to you. In fact, most of descriptive set theory doesn't actually work on the real numbers. That is, at the beginning, people were certainly using the real numbers, but by about 1950, people replaced the real numbers with a much simpler set theoretic object, which had sufficiently many of the properties of the real numbers that most of the things that you were doing would transfer across easily. And, you know, because it was simpler to deal with, you could prove more things, right? And this object was, it's denoted omega to the power omega, and it's the sequences of natural numbers, indeed. Okay, so here's a bit of a picture. This is only the binary tree, but you can see how this would carry on down. What you have to imagine now is, instead of branching 0, 1 at every point, you branch 0, 1, 2, 3, 4, 5, etc. at every point all the way down. And you get a nice thick line at the bottom, and that thing is the thing that descriptive set theorists actually deal with on the whole. Okay, but this is easy to generalize. Omega is a cardinal. You just replace it with a larger cardinal. And this is what people started doing even actually before omega to the power omega was widespread. People were doing this a little bit before then, actually. Okay, so I need to go through what this means. So recall that a cardinal is the size of an infinite set. So it could be the size of the natural numbers, it could be the size of the real numbers. You might remember this fact that there are more real numbers than there are natural numbers. That's this sort of thing, like what we say there is the cardinality of the real numbers is larger than the cardinality of the natural numbers. We can order these. Doesn't matter really what the ordering is, but it's injection without surjection. And if you order it in this way, omega, which is the cardinality of the natural numbers, becomes the smallest. Right, so natural question. What if you replace it with a larger cardinal? And that's generalized descriptive set theory. That's all it is. Asking the same questions from the first half, but on this larger space. Okay, so it's a topological space. It's ordered. That's nice. But it doesn't generalize everything about the real numbers. So, in particular, it's not a field. It doesn't have addition. It doesn't have multiplication. It doesn't have a sense of distance between points. So, is there something that generalizes the real numbers in a suitable way? So let's just track the story. We started with the real numbers. We moved to omega to the power omega. We generalized here. The question is, can we go back here somehow? Is that space occupied by anything?
Just one question. So generalized means
Generalizing. So in this case, it's a very good question. Generalizing has lots of different means in mathematics, but in this case, generalizing simply means we're moving from a certain size of infinity to a larger size of
the
infinity.
property of omega to omega, and then some of this property being generalized to kappa to kappa. Is it right to say?
That would be an example. Even more broadly, you could say that the whole field is called generalized descriptive set theory, and anything that takes place in generalized descriptive set theory generalizes things that take place in descriptive set theory. The word generalized is used all the time here. So, for example, the shorthand for this is Baire space. The shorthand for this is generalized Baire space, and so on and so on and so on.
And you need the last step to be filled?
Yeah.
What's the question?
The question is there anything here?
And you need it filled.
Yeah, a field. Yeah, exactly. So,
Not anything.
what are our demands? We have these demands. So, we want it to be a real closed field, right? So not just a field, we want to also take square roots, we want to take cube roots, whatever. And then we have the Cauchy completeness is also a sort of a requirement from analysis. So we want that.
Comes to the grey text very well. Can we turn off this sunlight?
Yeah.
The grey text generally is unimportant, extra details. But please. So Cauchy completeness here is all Cauchy sequences converge. That's another way of kind of showing that you're close to. How's that? Better?
Yeah, better.
Okay, close to the real numbers. And then these middle three conditions are all about making it infinite, but in the right way. So notice here, we didn't just have any size of infinity, any different cardinal. We've picked a particular cardinal, right? And in the same way, we want to pick a particular cardinal for the field. And we want that to come out in three different properties. So first property, size. So the size of the field needs to be correlated to the chosen cardinal kappa in the right way. Namely, it needs to be size 2 to the kappa, the size of the power set of kappa. This is in analogy to the real numbers. All of these are in analogy to the real numbers. The second one is about density. So recall that the rationals are dense in the reals, but the rationals are smaller in size. They're the same size as the natural numbers, but they are, between any two reals you have a rational, that sort of thing. So we want to have a smaller set which is dense within our field. And finally we want this length property. So the natural numbers form a kind of backbone in the real numbers. You're always close to integers, the integers really, but let's just think about the natural numbers for the moment. You're always close to a natural number. You can either take the natural part, or you can take the closest natural number, or whatever. And we want something like, and the natural numbers are smaller than the real numbers. We again want this. We want a backbone that is smaller in size than the field itself. Is there such a thing? Amazingly, yes. This was constructed in 2015 by Lorenzo Gagliotti, one of my PhD supervisors. His construction uses the surreal numbers. You don't have to do it that way. It's got a certain uniqueness property in the way that the real numbers have a certain uniqueness property given these definitions. The important thing here is that we've stipulated some conditions, and in fact they are satisfied by some object. Okay, so what's it like? This field, we call it R kappa. Because it's larger than the real numbers, it's going to have infinite numbers in it. So it's got this one, omega, which is the smallest infinity. But because it's a field, it's got 1 over omega, and this one, which I've written down, 1 over omega to the power e plus 5 omega. And this is the construction, not important, but it just gives you some feel for it. So 1 over omega is going to be less than all of the ordinary fractions, but bigger than 0, for example. So infinitesimal, if you like. But it's not all rosy. Some things are different. For example, unlike the real numbers, this R kappa has order theoretic gaps. And it has to, right? So think about this. The finite numbers are closed under adding 1. So you have a finite number, you add 1, you're still finite. The infinite numbers are closed under taking away 1. You have an infinite number, you take away 1, you're still infinite. So you've got these sequences, one decreasing, one increasing. In the real numbers, if we have a sequence, one increasing, one decreasing, you know there's got to be something in between. But in this case, there can't be anything in between. There can't be a least. Every number is either finite or infinite. There can't be a least infinite. There can't be a largest finite. So there's nothing in between. Okay, that's different. We're expecting things to be different. So there's a point of difference. There are actually lots of these gaps, but that's another story. These gaps cause strange properties in the function. So now we're moving towards the real analysis again. Okay, so we're going to think about the functions on this space. Yeah.
So these gaps don't mess with the Cauchy completeness?
No, they mess with the Dedekind completeness.
Okay.
But it's a good point. There are lots of forms of the completeness which are equivalent over the real numbers. It satisfies most but not all of them. For example, it satisfies Veronese completeness or Conway completeness, but it doesn't satisfy Dedekind, which is the one that says no order theoretic gaps. That's the strongest. The strongest one is no order theoretic gaps. It doesn't satisfy that. It satisfies essentially all of the weaker ones.
I just want to clarify, so
Yeah.
kappa here is a cardinal, right?
Yeah, fixed cardinal.
It's larger than omega 50?
Yes, yes,
So it's not just all human but cardinal.
yes. If you put in omega, you return the real numbers. Okay, so R omega is just the real numbers. Okay, so back to this. We've got this function. We've got this is a gap. This dotted line represents where there's a gap in the field. We've got a green function. We've got a red function. They cross over each other in a natural way, but they don't intersect. Where they should intersect, there is a gap. So we know that things are different. All right. And then we can start looking at kind of theorems of real analysis and see if theorems of real analysis from the classical case over the reals apply here. And this is some work that I've been doing. This is the last part of the talk. I'm just going to mention the 3 broad cases. So broad case 1 is, and I'll do an example of each. Broad case 1 is, it generalizes, it works. Broad case 2 is, it doesn't generalize, it doesn't work. And broad case 3 is, it depends on the size of infinity, it depends on the cardinal that you chose at the beginning. And that's perhaps the most interesting case. Okay, intermediate value theorem. This is the one which says you're continuous, you go through here, you go through here, you have to go through there. Okay, that's you have to go through at some point in this segment. You have to go through that point. Right, intermediate value theorem. Does that apply? Well, for trivial reasons, it fails for continuous functions. So you can here is a continuous function on R kappa. Well, that's a gap. You can have these so-called jumps at gaps. So what you have is a function that is here and then it's here. It's jumped at a gap, right? That's continuous according to the standard definition of continuity. Somehow these jumps are invisible to standard continuity. Okay. So what's the lesson we take away from this? Do we take away from this that the intermediate value theorem fails? I would say that the lesson we take away from this is that standard continuity is not the appropriate notion for this new field. These jumping functions are an example of that. We don't want this to happen. That violates the sort of naive definition of continuity of pen doesn't leave the paper. What you can do is give a very, very mild strengthening, generalization of continuity, so-called kappa continuity. Definition is important, but it's quite simple. It's very close to continuity. And then the kappa continuous functions they satisfy the intermediate value theorem. So what we've done here is we've observed the trivial problem, we've made a minor generalization, we recover the theorem of real analysis. All right. So, hooray, we've got kappa continuity and everything's looking rosy again. Except no, some things don't work. Right, so, remember right at the beginning, we said sometimes classes of algebras are closed under nice properties. One of these classes is the continuous functions, and they're closed under addition. You pointwise add two continuous functions, you get a continuous function. Still works for continuous functions on our kappa, because that's a general fact about continuity, not about particular fields. But we've sort of abandoned continuity. So what about kappa continuity? Do we recover this? Sadly, no. We can set up examples where you've got two kappa continuous functions, and you add them, and you get a function which is not kappa continuous. So red is the identity. F1 is a cleverly chosen function. You add them, you get this green function, which is one of these jumpers, and if it jumps, we know it's not kappa continuous. Okay, so now we've got a tension. On the one hand, we had continuity, which is nice because it's closer to the classical case, and also it satisfies this thing, it's closed under addition. On the other hand, we have kappa continuity, which is nice because it's close to the naive notion of continuity, the pen on the paper notion of continuity. Right. So I would say that at least prima facie, pen on the paper continuity is more important than this. You might say, well, this shows kappa continuity is a bad definition. But I'm not sure that being closed under addition is kind of the most important property of continuity. Anyway, that's my argument. And here's the final example, last bit. So these two cases we've just talked about don't depend on what kappa you chose to begin with. Any kappa will do. Now we have cases where it depends on the kappa that you began with. All right. The particular statement is kappa has the tree property if and only if sharp functions have extreme points. That's not very helpful. I'm going to say what those definitions mean, roughly. All right, cardinals. The sizes of infinity, they themselves have mathematical properties. We saw that picture before with this network of increasing notions of properties of infinity. This is kind of what set theorists, rather than descriptive set theorists, spend a lot of their time doing, thinking about properties of cardinals. I've said this, some generalizations of theorems depend on whether your chosen cardinal kappa has one of these properties. Typically, it's a combinatorial property. So what's a combinatorial property for a cardinal? It's you take your cardinal, you make combinatorial objects out of it, so trees, graphs, networks, and then you ask about the properties of those things. For the tree property, which we care about, you ask about the trees. And if those have certain combinatorial properties in analogy to the finite case, you just declare, we define this tree property for the sizes, for the cardinals. Okay. Now, the extreme value theorem generalizes to R kappa for a certain other mild strengthening of continuity, so not kappa continuity, but quite close to it, if and only if kappa has the tree property. I think this is remarkable. So on the one hand, we have a property of sizes of infinity. And on the other hand, we have a property of functions on some field. And yet it turns out that these are exactly the same statement. Your functions on the field behave like they do in the classical case if and only if the cardinal which you plugged in at the beginning has this totally apparently independent property coming from combinatorial objects. So there's much more to say in this. I hope I've persuaded you that it's an interesting thing to pursue. I hope that even some of it might have made sense. Thank you very much.
Is there some question or comment?
Yes, I have a question.
Please.
How can one modify this capital continuity so that it becomes additive?
Yeah, I wondered about that for a long time. You can strengthen it so that you do have this additivity, but so far the proposed strengthenings are so strong that you're almost just talking about semi-algebraic. It's like we've gone right back to in the 18th century where we're just talking about trigonometric and algebraic and so forth. I believe there should be an intermediate one. I haven't found it. My colleagues haven't found it either.
Other question? Comment?
So you mentioned like the three theorems like
Yes.
So all these three theorems are not holding like force, like apart from things. So is it like applying to the omega like is like the kind of like like borderline that all these things are
So is the question when do theorems always hold? Yeah, as far as I know, only omega. There does seem to be it does seem that omega is somehow a special case. You can get quite a lot of theorems to hold. Okay. If you go through a calculus textbook and you list all of the named theorems, this is quite a good test. You know, if it's sufficiently important that someone's name is stuck on it, you can normally get all of those to hold on a single field, but you need your cardinal to either be omega or extremely large. So it's somehow omega is odd in that even though it's very small, it's got all of these very large properties because it's the first one of the very, very large things. So yeah, that's something you can do. But with these things like additivity, no, only omega. Only omega.
So I have a question. So it has been long that I learned from someone else that if you throw away axiom of choice,
yes,
you can build a real model such that every set is measurable, right?
Yeah.
So is this statement somehow can be put into
yeah. So
is this a descriptive set theory problem or?
Yes, one of the things that you can do in descriptive set theory is vary your set theoretic axioms, and the most interesting one to vary is the axiom of choice. The model that you mention, so this is a model that satisfies all of the other axioms but doesn't satisfy choice, and the amount of it doesn't satisfy full choice, and the amount of choice it satisfies is very small. So it's sometimes called the analyst's paradise, this model, and because the thought was that it would be brilliant for analysts. It was kind of developed in the 60s, and the set theorists who developed it thought, okay, now all of the real analysts are going to work with this model forever. And it turned out that actually real analysts preferred having the axiom of choice. It's sufficiently involved, this work, that no one has yet looked at what happens when you don't have the full axiom of choice. Some of the cardinal properties, so a notable one would be measurability or weak compactness, either of those, are so strong that they're actually above standard set theoretic assumptions. So rather than looking at lower than standard set theoretic assumptions, weakening choice, for quite a lot of this work, you have to go higher than the standard assumptions. I would be very interested if people could develop this on with weak choice and looking in the analyst paradise model, but I haven't done it. No one else has, as far as I know.
Are there other questions?
I have one question about the hierarchy of the set. Do we have some simple example or some simple method to construct level 3 but not level 2 set, level 4 but not level 3 set, and some goes on, something like that?
There's no, now let me say, I am not aware of an algorithmic way of making one of arbitrary high levels, but for the low levels there are particular known sets. Then the problem is they're not very insightful for the higher levels. They're things like collections of limit points for certain functions. And you can say, you know, and then you do a bit of proving and you realise, okay, it has to be level 3 or whatever, but it can't be level 2. I don't think it's that insightful for the higher and higher levels. The proof that there are these things, that the levels are actually strictly increasing, is a general proof. It doesn't you know, give you an intuitive set at each level. Yeah, for the bottom levels you can find them, basically.
Other question or comment? If no more questions, no more comment, let's thank Ned again. Thank you.
Thank you. Thank you, everyone. And I'll be here if anyone wants to ask a question less publicly.
Yeah.
Cool.
Thank you.
I should have seen if there are any on here. No, there are no comments on here, so that's easy. Okay, I'm going to close this off. Oh, is there one comment? How do I see it?
No, yeah, no comments, right?
But then it says one comment here.
That's weird.
Oh, there's 0 comments again. Okay, fine.
Okay, yeah.
Nice talk. Oh, thank you. All right, I'm going to end this.
Yep. Alex.